All right, so there's two big topics really in this section, direction fields and Euler's method. And even though Euler's method seems more complicated, it's definitely more computational, more intimidating. It really boils down to a formula. And if you've seen one, they're pretty much all the same. So I have one planned towards the end here. We'll do an Euler's method problem, but I think what maybe is more confusing and certainly anticipate lots of questions, or at least maybe more than one question on your short test. I keep thinking we're doing regular tests, but on a 24-minute test, maybe one question on direction fields. And so we're going to talk about it. We'll talk about how to generate a direction field. Although I think she even hinted in class, that takes a lot of time, as you saw. It's pretty time intensive. So more likely would be to be able to, for example, if you were given an option of 4 direction fields for a particular differential equation, maybe figure out which one goes with which. But in order to understand that, it is worth thinking about how one of these would be generated to begin with. So that's what we'll start with. And I want to start with one that should be kind of familiar, because one of the growth models that we were talking about, I had it in terms of n, was something like this: r times n, 1 minus n over k. And that particular growth model describes what we call logistics growth. The idea that there's some maximum carrying capacity, right? And so this I have different variables, but hopefully you see this is the same thing. This is going to be describing some kind of logistics growth. And I chose that because, number one, we kind of already know, if you've been coming, sort of what a solution would look like for a logistics growth problem. So we'll be kind of confirm with, as we sketch the direction field, we'll kind of confirm that it's the graph that we're expecting to see. Okay. And truthfully, I know this seems surprising, but Dr. Burke has spared you so far, because there certainly are problems. This is a separable differential equation. You actually can solve something like this. What ends up happening, though, if you move the dx over and divide these two y factors over underneath the y, you end up needing to use partial fractions, which is something we've done, but it just gets kind of long and tedious. So I haven't seen so far, at least even in the suggested problems that she assigned from 7.4, her expecting you to solve this, actually, even though it is solvable. So I just put this note: it is difficult. And so the idea of a direction field is to visualize the solution without actually solving it. So you can kind of predict what's going to happen if y was representing a population, right? Like I always like to give it some kind of context, maybe a population of owls today. How about that? Okay. And then the idea, you see what's happening when you do a direction field, is this formula is equal to dy dx, which tells you what about our solution? We know dy dx from 17a tells us the slope. It's the slope of our solution at any particular point. And so a good place, I think, to start, if you're sketching a direction field, is to find out any places where the slope is equal to 0. Right? Which, how would I do that? Well, if this is the slope, I'm going to set this equal to 0. Maybe I can do this in purple. 0 equals 1/2 y, 1 minus y over 10. And notice this is exactly the same thing you would do if you were being asked to find what? The two values of y that make this true, one of them would be y equals 0. The other one would be y equals 10. And those would also be known as what for this particular differential equation? Yeah, those would be equilibrium points, right? Okay, so we're setting this equal to 0 right here. So these are equilibrium points. But if you're sketching a direction field, there's a little more to it. This might be helpful because I'm going to introduce a term that I haven't heard used yet, but you certainly will hear this all over the place in 17C. Okay. What this is saying is any point where y is equal to 0, I'm going to have, my solution is going to have a slope of 0. So not just, so I'll put them right, any point along these, we're going to think of these as, these are equations of lines, right? Y equals 0 is the x-axis, y equals 10 is a horizontal line. Any point along, that's an A, these lines, the solution has a slope, I'm having trouble writing today, slope of 0, which means it's going to be horizontal. And the word you'll hear for this at some point, whether it's this quarter or next quarter, because all these points have a slope of 0, these are sometimes referred to as Nullclines. Think of like if you're going up a hill, you would maybe call that an incline, right? Incline kind of means you're going uphill. If you were declining, you would be going downhill. Null kind of means nothing, right? There is no incline or decline. Okay, and these are called Nullclines. Don't recall her saying using that terminology yet, but. And so here's what I know. If I'm going to sketch my solution curve, I've got some axes right here. Y equals 0 is the x-axis, so I know. Oh, and I should give, let me give this some points here. Let's go like 1, 2, 3, 4, and so forth. And actually just thinking ahead, because I know I'm going to need y equals 10, let me use a different scale on the y-axis. We'll go by 2s. How about 2, 4, 6, 8, 10, 12, and 14. And so as you've seen, what a direction field looks like is just a bunch of dashes. They're actually meant to be what we call vectors, which is coming up. That's the next chapter. How many people know what a vector is? Like a little line with an arrow. A vector is usually, like if you've taken some physics, it's like a line with an arrow. But we're not putting the arrows on yet. So basically, any place along y equals 0 at any given x value, you could imagine a bunch of just horizontal little dashes. Same thing at y equals 10. Anywhere along this line, you can imagine your solution is going to be horizontal. So we just draw a bunch of dashes here, horizontal. And so already I've generated, because you saw one of the troubles is you could pick points, you can pick x and y values one by one and generate just one of these individual arrows or lines. So it's really nice when you can generate a whole bunch of them all at once. Okay. And there's different strategies for generating these slope fields. And some of it, I'll be honest, depends on what kind of a differential equation I'm looking at. Notice in this case, my differential equation I wrote right here, it really just depends on my y values. The slope I get does not depend on x. It only depends on my y values. This is, okay, more terminology. You've learned this before. What kind of a differential equation, if you had to classify this? Is this autonomous, pure time, or mixed? Oh, we're ready for that question, huh? Yeah, reminder. So autonomous means that, if we think of this again as, let's give it context. If this is measuring the growth of owls over time, the growth rate of owls over, okay, I know usually they use they use X, but that could be easily T, right? The growth rate of owls over time, notice it's strictly a function of the owl population of Y. So this is autonomous. If you get an autonomous differential equation where your slope is just dependent on Y, then you could, I think the best way to do it is to just pick some different Y values. For example, if Y is 2, what I'm going to get for dy dx, I'm going to get 1/2 2 times 1 minus 2/10. I just put in y equals 2. And that's 1 times 1 minus 2/10 is 8/10. 8/10 reduces to 4/5. And here's how I can use that. What that tells me is, here's y equals 2 right here. And notice that it doesn't matter what x is. So I could even put y, and then I could just really just put here, x can be anything, right? Any number, doesn't really matter. But anywhere where y is 2, which is everywhere along this line, I'm going to be seeing a slope of 4/5. So slope, that's a little bit less than 1, isn't it? 4/5. 5/5 is 1. So I don't know, maybe something, it's all about like kind of guesstimating, maybe something like that. I'm just estimating this is a slope of 4/5. Everywhere where y equals 2, I'm going to have the same slope of 4/5 there. If y is 4, dy dx, I'm running out of room here, is going to be equal to 1/2 4 times 1 minus 4/10. Help me out with the math here. That's 2 times 6/10 is 12/10, which I believe reduces to 6/5, which is a slope a little bit bigger than 1, so steeper than this one. So everywhere where y is 4, I can picture just a slightly bigger, steeper slope here, right? Maybe something like this. And see, these ideas where you can get lots of slopes easily, right, are really, really useful when you're sketching slope fields. All right, I wanted to do a couple more here just to show you. This is 1/2 times 6 times 1 minus 6/10. That's 3 times 4/10. 3 times 4/10 is also 12/10. So this is also 6/5. So I have the same slope here. I was trying to match this row here. So if it doesn't look right, that's okay. Well, again, it's not a perfect thing. It's 4 times 2/10 is 8/10, which goes back to 4/5, which is back to not being so steep at 8. So that's maybe more like this. I was trying to match these slopes here. And see, already, just with what we've done here, because one of the things, this is the other thing I fully anticipate being on there on your next short test is you will get already a computer generated one of these and asked to just sketch a solution curve that's passing through an initial condition. And that's super easy. If this shows up on the test, it's going to be the easiest question on there. Okay, because all you got to do then is just imagine if you're starting y of 0 equals 2, you're starting right here. You just have to imagine imagine these as like arrows, and they're pointing you towards where you want to go. And I can see here that it's telling me to kind of go upward. And then when I get here, I can tell that's telling me to go steeper upward. And then this is telling me not so steep anymore, right? Right here, these slopes. And then I know by the time I get to here, my slope should be getting more and more horizontal. So I can tell my solution curve through 0, 2 should look like that. I like to think of these as like I don't know if you've ever gone on a river, like if you've ever gone rafting or something like that, you may notice that like the flow in the river is different at different points, right? And it's kind of like these are telling you the direction of the current and where it's kind of pushing you, and by the time you get here, it's pushing you directly to the right. So you just kind of imagine your path if you were a boat in this river. And then what ends up happening, like I have one more sketch a curve, but this one's starting through 14, which so I just finished this off. If you keep plugging in values here, 1/2 times 12. I think this comes out to be -6/5. And if you try 14, it's going to come out to be -4/5. I don't want this whole class to be just plugging in numbers here. It's going to be -4/5. And so what ends up happening, maybe if I move this out. Kind of can fit it in there. Oh, wrong way. So everywhere at 12, I'm going to have a steep negative slope like this. And then at 14, it was not quite so steep. It was like -4/5, so not quite as steep in a negative way. Did I do that wrong? 6 times, no, that's right. Why does that feel wrong? Why don't I actually do it? 1/2 times 14 times 1 minus 14/10 is 7 times -4/10. Oh, that's -28/10. Never mind. This is -14/5. My bad. My bad. So this should actually be even steeper. These are actually more steep in a negative way. And what you can kind of then picture is, maybe I'll do this one in red. Everybody catch that? The slope at 14 actually should have been even steeper in a negative way. But you could kind of picture then your solutions going pretty steep this way, not so steep. And then knowing that this is eventually your slope has to be getting closer and closer to 0 slope in a negative way. So your solution looks something like that, starting at 14. Okay, let's try another one here. How are we doing on that one? Okay. Wait for a second. Let's do. So the first thing I would do normally if I'm sketching a direction field is to find my Nullclines, because those are just easy points that I'm going to want to add to my graph here. Nullclines are where dy dx is equal to 0, where I have a horizontal tangent line. So that would be y times 1 plus x equaling 0. This time my Nullclines are either y equals 0, we had that before, or x equals -1. And so I decided not to use any negative y values here. We'll just focus on positive y and positive and negative x. So here's -1. Let's go 1, 2, 3, 1, 2. Go to -2, let's say. Okay. So what this tells me then is, in addition to y equals 0, which is the x-axis, I know my direction's 0 there. I know I'm going to have horizontal little vectors or hash marks there, but also along the vertical line -1. Anywhere along this vertical line, which is going straight up, my slope is going to be horizontal. But that doesn't help me that much in this case here, right? That doesn't help me really figure it out. So what I would want to know then, the way I'm seeing it is, I mean, if I don't care about negative y values or whatever, I want to know what's happening to the right of -1, right? Are my slopes going to be going up now, going down? What's going to happen? And also probably to the left of -1. And so sometimes after I do my nullclines, I just ask myself, well, now what do I want to know? Where do I want to see what's happening here, right? So this is hard to fit in on one screen here. So that's why I wrote this down. Let's see what happens. Okay, I started with the left, or to the left and the right of the nullcline x equals -1. And so here's what you could do. You could let x be -2 in my, oh, I forgot to ask, but this differential equation is a mixed one, right? My slope is a function of both y and x. Y and x. So if I want to let x equals -2, I could potentially get different slopes depending on what I choose y to be. So that's why I left this blank. So let's see. What if y was, well, we already know when y is 0, it's 0. So how about y equals 1, 2, 3, 4. I want to see what my slopes look like if x is -2, so over here, but at different y values to see what's happening here. And it's really easy to do because remember my differential equation was y times 1 plus x was dy dx. So if I have x fixed at -2, I can just put -2 in there. And dy dx will be y times 1 minus 2, which is really just -y. And so what I've quickly figured out all at once, along this line, x equals -2, when y is 1, my slope will be the negative of that. It'll be -1. When y is 2, it'll be -2. So, -1 here, I'll draw a little sample. That might look like this. -2 is a little bit steeper, right? -3 is even steeper than that. This is going to be -4, which is at some point I can't draw them any steeper, but and so I can take these slopes and add them to my picture. X is -2 and y is 1. My slope is -1, so that's kind of a gentle negative slope. This one's -2, a little steeper. Even steeper. Steepest. So I can kind of see now that if I was starting over here, my solution's going to go down, but then it looks like it's going to go horizontal here, right? If I were to interpolate in between, my solution would go horizontal. And then maybe what I want to know is it going to go up? Is it going to go down from here? So let's see what happens when x is 1. Let's see what happens over here. Or I guess I could have done x equal, oh, wait. No, these weren't marks. These were just my marks for the, okay, that's it. We could also try y equals 0 here. Let's try y equals 0. Let's see what happens right here. These are not the vectors. These are just the marks here. I shouldn't have done that. They should just put points there maybe or something. So let's find out. I made a little table here. What happens when x is 0, which is along the y-axis, and y can be any number. So why don't we pick y equals 1, 2, 3, 4 as well. And notice that this time my differential equation, which is y times 1 plus x, if x is 0, that tells me dy dx is just going to equal y. It's going to equal whatever my y value is. So if y is 1, my slope is 1, 2, 3, 4. Positive, more positive, even more positive, even more positive. So then I could come back here and go kind of positive here, steeper positive, even steeper, steepest, at least for the ones we've done here. And then you can probably see what's going to happen. Like if you wanted to keep going, you could consider what happens when x is 1. If x is 1, then your differential equation is going to turn into y times 1 plus 1, right? If x is 1, which means it's going to be 2y. And then you could kind of see, well, if x is 1, the bigger y gets, I'm going to get steep slopes, right? Because my derivative is going to be dy dx is going to be twice y, right? So you could picture these being even steeper, right? This is even steeper, even steeper, even steeper than that. And you can kind of then piece together what this direction field might look like, which would be, if suppose I were to give you an initial condition. So maybe on the actual short test, maybe she says, maybe you'd have for sure a computer generated one, so you'd have more arrows than I have. But if she said this was your initial condition, like right here, and sketch the solution, what would happen? You're just following the arrows. The arrows are taking me down. And it doesn't have to be perfect, right? Down at some point, these are getting horizontal. And then this is telling me my solution is going to go upwards. So it looks something like that. Don't worry about, if you do this and someone else has it crossing right here or down here, that's all just kind of estimating. So it doesn't really matter so much. It's more about the overall picture. In the interest of time, I think I'm just going to pose my next question, and then we can, we have Wednesday to come back and revisit some of these, because the whole idea of a direction field is you're trying to predict what the solution might look like without actually solving the differential equation. But part of what you're going to be tested on Friday is solving a differential equation. So the question I have is, how would you solve that if we were going to solve this? I don't think I want to do the whole thing because we've done that before. And I think really we want to focus on direction curves and yeah, give me 1 second. Let me finish this question here. So how would you solve this? Okay, having said that, here's the good news about Friday's test. If you get asked to solve a differential equation, you have 2 methods now at your disposal here, right? We have either separation of variables or the first order linear thing, right? The integrating factor. Good. And what I'm seeing in there is, this definitely looks separable, especially when they're multiplied. It's usually separable. If I just multiply the dx over to the right side, that would give me dy equals y times 1 plus x dx. And then see, I have my 1 plus x where I want it with my dx, and all I'd have to do is divide by y, and I'd end up with dy over y is equal to 1 plus x dx. Once you get them separated, integrate both sides and go on here, right? So this could be solved with separation of variables. Okay, so probably for practice, that would be a good thing to go through and finish that, make sure you could do it. But we want to practice sketching solution curves because I wanted to give you, solution curves, direction fields. I wanted to give you one other strategy for sketching direction fields that I don't think was mentioned either. One of them is the Nullcline. Definitely, I think I would always start with that. For dy dx equals x minus y. By the way, since I just asked how to solve this one, how would you solve this one? Is this one separable? I'll put a little. Yeah, it's not going to be separable because if you multiply the dx over, if you try to go dy is equal to x minus y times dx, see, you can't, there's no way to get this y term over to the dy without bringing the x with it, right? You'd have to divide by x minus y. And then you'd have the dilemma, you have your y over there, but you also have your x over there, which it needs to stay here. So you can see just by doing this that this is not separable. But if you viewed this as y prime equals x minus y, move the y over to the other side, how many people see this as a first order linear differential equation, right? That has the form where your p of t or p of x is just the 1 here, and your q of x is x. So you could solve this, also good practice. See if you can solve that later on. But let's think about the direction field here. My Nullcline this time, if I set dy dx is equal to 0, is just going to be 0 equals x minus y, which is y equals x, not y equals 1, y equals x. And so, sorry, I know this is going to drive you nuts. Somewhere on your paper, go ahead and start to sketch we're going to sketch our direction field here. You can already, and I just have it going from 0 to 5. And we're only going to do the positive x and y values. Because what I know now is every point on my direction field along the line y equals x, you know that line, y equals x passes through 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Everywhere along here, I know my solution has a slope of 0. So I know my arrows are going to be going horizontal here. And so another strategy to do here, I couldn't have done this on the last one. Well, I could have, I guess, but see, given that my slope is a function of x and y now, right, together, x minus y, what if I instead choose different values for my slope and find all the points where I have different, a specific slope? So say, for example, I wanted to, well, I already know this, right? When dy dx is equal to 0, all the points that are going to generate that lie along the line y equals x. But I could also find all of my points that have a slope of 1 by just setting 1 equal to my differential equation. So remember, my equation is dy dx is equal to x minus y. So I'm just picking values for dy dx and setting my equation equal to it. Now, this is easy to solve for. If I move the y over here, subtract the 1, that gives me y equals x minus 1. And that tells me everywhere along this line, I'm going to have arrows that have a slope of 1, right? A slope of 1 is going to look, maybe something like this. So let's add that. Y equals x minus 1 would be a line that actually goes down 1 and up 1 over 1. So it's going to be all of these points right here. It's just basically y equals x shifted down 1. So every point here, just go down 1, 1 unit. But now every point along here has a slope of 1. So you can picture your directions arrows going that way. This is y equals x minus 1. This is along y equals x. And we could just keep doing this. So if I set 2 equal to x minus y, that gives me y equals x minus 2. And a slope of 2 is a little bit steeper. Y equals x minus 2 would just be drop down 1 line, 1 unit here. So that would be like these points. And these points have a steeper slope through them. And probably a good idea if you're going to do this strategy is like, pick some positive slopes, but also pick some negative slopes. If I want to find where all my points, where my slopes are -1, that's going to give me y equals x plus 1, which is directly above. Remember, this is y equals x. This one was y equals x minus 2. So y equals x plus 1 would be going through here, here, here. And those slopes are kind of negative now, -1. And then one more, y equals, if dy dx is -2, that gives you y equals x plus 2, which is just above again. And these slopes are more negative. But m equals -2. This is m equals -1. This is m equals 0. This is m equals 1, right? And these are just the slopes. And see, then it would be pretty easy now to see if your initial condition was, let's say right here, this was your initial condition, what do you think the solution would do? I'm seeing something kind of like this, curving down, but then getting horizontal here, right? Horizontal right along this line. And then it looks like possibly just starting to approach y equals x minus 1. All right. I'm already thinking of some good ideas for Wednesday to help you practice this idea of the direction field. But what I would recommend now is do some of those problems where you actually by hand have to sketch the direction field. And you can check them, by the way. You can find, if you look online, you can find I would look for direction field plotter. I was going to share one with you. So if you want to check later on if you have the right thing, even Desmos will do it. If you put in slope field generator, it's telling you to type in a formula for the derivative, whatever formula they gave you. This is going to be my next example, x plus y squared. You can see it'll generate these little lines for you as well. So if you do some of those problems in the book and they don't have the answer in the back, you could always check it with a calculator. All right, I think I have enough time. I might go over a tiny bit, but to introduce Euler's method. And that is Euler, not Euler. That's what I always want to say, but it is Euler. And what Euler's method is really, really, really powerful for, I heard her say, you're going to be, if you go into research, you're going to be doing Euler's method at some point. All of the examples I've talked about so far, I've showed, well, we could solve it, right? The one we just did is a first order linear. We could solve it. If you can solve a differential equation, why would you, without too much trouble, then there isn't really a compelling reason to draw a direction field other than to maybe avoid some work like my first example. But there are plenty of differential equations that there is no way to solve this one. Check this one out. If this had just been t plus y to the first, that would have been a first order linear differential equation. But because my biggest power of y is y squared, that actually makes this it's still a first order, but what we would say here is either degree 2 or quadratic. Okay. It's not linear because of that term right there. That's what we mean by the linear part. And in the world of differential equations, if you go on and you take another course in this, there are techniques for actually finding the solution if it's first order quadratic, but we're not going to learn it in 17b. And let's say we want, we can draw these direction fields, but that doesn't give me actual data, doesn't give me actual numbers, right? It just gives me an idea of what the solution looks like. So if I actually want an approximation to the solution of this differential equation at some value, in this case, I want it when t is 2, Euler's method can help us approximate that. And I think it's helpful to think about, I'm going to approach it maybe the opposite way. Rather than give you the formula right away, I want to show you what's going on and how you can think about Euler's method. And then we talk about the formula, and it's pretty easy to use the formula once you know what everything means. Okay. So let's assume that, let's pretend this was the actual solution to that differential equation, which is our whole problem, right? We can't find it right now. Okay. What Euler's method essentially does, let's see if I can do this in maybe green will probably work. What Euler's method essentially does is you saw this thing about a step size. Ultimately here, the question posed was to find the solution when t is 2. That's what that means, when t is 2. But the way it works with Euler's method is if you start with an initial condition of 1, we're going to take it in steps. We're going to see what the solution looks like at various points and then finally end up at 2. And the smaller these steps are, these widths, you get a more accurate answer, just like with integrals, right? When we were doing delta x, the smaller the step size, you get more accurate answer. But if you make the step size smaller, that means you're going to need to do a bunch of individual steps to get to your ultimate destination, which in this case is 2. So typical problems on tests and homework and stuff, you may have to do 4 steps or 5 steps or something like that. So here we want a step size of 0.5 to get to t equals 2. So you can tell we're going to need 1, 2, 3, 4 steps. And here's essentially what happens. Because the differential equation dy dt, we already talked about, that's telling us slope, right? This is telling us slope, the slope of my solution. We're going to capture the slope at different places. We'll talk about the actual numbers in a second, but in other words, I could use my differential equation to find the slope of this solution. Even if I don't know what it looks like, it'll tell me it. And then the idea is, whatever that slope is, you follow that slope for a distance of 0.5. You follow this straight line. And this point right here is going to be called, we'll call this T1, Y1. Then you want to know what your new slope is. And so you could plug in 0.5 into your differential equation. It will now give you an updated slope, which you can tell right here is steeper. And so we'll pick it up from here and we'll follow a slightly steeper slope until we get to 1. This point here we'll call T2, Y2. But we need an update. So then we'll plug in 1 into the differential equation and we'll find our new slope actually is a little steeper here. So whatever this slope is, we'll just follow that slope for a little bit. And then finally, we'll get the slope at this point, and it's going to be a steeper slope as well. And when we get to 2, I guess that's probably about right here. This would be what we want, right? This would be your 4th iteration of this. And that would be the point we want. Now you can see that when I'm going to be using this as my approximation for the actual solution when y is 2 is up here. So in my picture, I'm getting an underestimate for sure, right? But at least it's an estimate. In fact, you know what this reminded me? I had this was the first time I've thought of this in how many years of teaching this. You know what this reminds me of? What's that game you play? I don't know why I played it as a kid. Every kid plays this in the pool when you got some friends when you were younger. Somebody's It. How many people have played Marco Polo in the pool? If you're familiar with that game? Okay, because that's what it makes me think of. You are blind because we don't know. The reality is I don't know what this solution looks like. So you are blind and you basically, you know, when you play Marco Polo, somebody yells polo and you start moving in that direction and then you're lost. And then you say Marco and somebody says polo. Oh, now I know I need to go in this direction, right? And then someone says Marco. Oh, now I need to go this direction. It's exactly the same concept as Marco Polo. Every time here, we're getting a new update of what direction we should move, right? Just like somebody yelling and you know where to follow their voice. And effectively, that's what this equation does. This is, you remember this from 17a, this is a recursive sequence. It's telling me how to get to the next y1, my next term based on the previous one. And it has, so it's yn, this h is my step size, so h would be 0.5. I left this blank here because you were supposed to figure out that it takes 4 steps of 0.5 to get to 2, right? If you start at 0. And then this is my differential equation. This is what's going to give me my new slope, my updated slope. And this tells me to follow it for 0.5 units long from my previous spot, right? Previous spot, how long I follow it, what's my new slope? Now, I will say this. Sometimes unless you get a really nice differential equation, the numbers are going to get messy at some point. And so I don't know how you handle that on a short test. Maybe there's a way to come up with an equation where the numbers really aren't that bad. I imagine if I put some time and energy, I could do that. But anyhow, if I want to find this first y1, what I would do is I would start with y0, which was my original y value of 1, plus 0.5, and then I plug this coordinate 0, 1, I plug it into my differential equation, which I think I want to write. I'm going to write it up here. It was t plus y squared. This was my differential equation. And so I would go 0 plus 1 squared, which is just 1. And 1 plus 0.5 times 1 gives me 1.5. So this point right here is, now I know that 0.5, 1.5. I want to now find what y2 is. I need an updated value. So I'm going to go y2 would be equal to y1 plus 0.5 times f of this value, 0.5, 1.5. And this is where things are going to get messy because y1 is 1.5 plus 0.5. And then my equation is t plus y squared. So it'd be 0.5 plus 1.5 squared. Yeah, at this point, this is not a reasonable quiz or test question because I don't think you'd be expected to do that without a calculator. So let me just show you the numbers. I already worked this out. This comes out to be 2.875. And if you keep repeating this process, this would be y2 plus 0.5 f of, it helps me to go back here and label this point. This new point now is 2.875, because that's the one I'm going to be using, be plugging into my differential equation is 2.875. So that's going to equal y2, which is that. And then it's t plus y squared. So 1 plus 2.875 squared. And I got a value of 7.51. Okay, in the interest of time, if you do it for y4, what I ended up getting was, actually, it's very big, 36.44. And see, that's my estimate. What does H represents the how far you're moving. It's the step increment, which will be given to you. I heard that asked in class. That will be told to you in the problem. You don't have to guess this. This will be given to you. They're going to tell you the step size. And that's basically how, if you're starting at 0, how many little increments you need to get to whatever number you want. And this would be my approximation. So 36.44 is my approximation for the solution, the actual solution, right? Evaluated at 2. 2y of 2 is the actual solution. So it's my approximation for what y of 2 would be. So I'm going to have to, between now and Wednesday, I'll do a little thinking to try to see how could I ask a question like this where the numbers just don't get really too crazy. Okay, I'll try to dream up one that's a little more reasonable for Wednesday. We can practice this. Did everybody need to see the bottom? Sorry about that. Okay, I'll stop here.